Let me know when I should start.
Yeah, so just as a brief preamble, I wanted to say just a little bit. This is sort of a historical talk. We think that it's good for mathematicians, physicists, and more broadly scientists to do these kinds of historical talks to give some kind of insight into what they were thinking when these developments occurred, many decades ago. It's especially easy, I think, to sort of reinterpret past developments in present terms, to forget things and to otherwise obscure how ideas developed. And so this is kind of our attempt to ask researchers who were involved in the original work to sort of present their ideas with this kind of some kind of historical background, some kind of historical insight into what they were originally thinking when they wrote these conjectures, papers, whatever else. And so, yeah, I would like to welcome Douglas Ravenel. Thank you very much for being here. He's going to talk about the Ravenel's conjectures.
All right. Well, thank you very much for the invitation, and I like what you're doing. I think trying getting historical perspective on things like this is a very good thing. So I'm going to begin. This history is going to begin in the well. Here's maybe what you might call prehistory. A standard problem in topology is the following. You've got two topological spaces, and you'd like to know what all the continuous maps are from one to another. Now, this is way too hard. This is an unreasonably hard problem. So algebraic topologists simplify this problem by saying we're not going to try to list all the continuous maps. We're just going to classify them up to continuous deformation. And there's a definition for that. And that is, we'll say that two continuous maps from X to Y are homotopic if there's a continuous map from the product of X with the unit interval into Y, such that when you restrict that map H to either end of the unit interval, you get the two maps that you started with. So two maps are homotopic if you can construct a map H from the cylinder X cross the unit interval into Y with the right properties. And it's not hard to show that, let's see, that map H is called a homotopy. And it's not hard to show that this gives you an equivalence relation among continuous maps from X to Y. So you can ask about the set of homotopy classes of maps from X to Y. And this is typically denoted by square bracket X comma Y. So that's the set of homotopy classes, equivalence or maps defined up to continuous deformation in the sense that I've just defined. Now, let's consider the case where one of the spaces is the m-dimensional sphere. That is the set of unit vectors in Rm plus 1, Euclidean m plus 1 space. And as there's a standard topology on Rm plus 1, so the sphere inherits the subspace topology from that. And so we could look at the set of maps, homotopy classes of maps from Sm into some other path-connected space Y. And it turns out that this set has a natural group structure. And not only that, this group is abelian if M is at least 2. And this is known as the nth homotopy group of Y, and denoted by pi m of Y. And this was first defined by Witold Horowitz in 1935. Now, fundamental problem in homotopy theory is determine the homotopy groups of spheres. So we're interested in the case where both X and Y are spheres of various dimensions. Now, this problem has been around now for almost 90 years, and it's an extremely hard problem. It has occupied some of the best, it's been the subject of some of the best mathematical work in the subject for these 90 years. I do not expect this problem to be solved in the lifetime of my granddaughters. They're 6 and 10 at the moment. I do not expect this problem to be solved in their lifetime. Now, I heard about this problem when I was in graduate school. And a short time later, I found myself hiking in a desert in the Middle East, and I came across a magic lamp with a genie inside it. And this was the conversation I had with the genie. I'm the guy in the green shirt. Now, I'm going to talk about three things that were three developments in algebraic topology that were being discussed in the early 70s. That this was the context, the historical context in which these conjectures were formulated. So I'm going to talk about three things that were three things that caught my attention back when I was soon after I finished graduate school. So one of them is complex cobordism and the Adams-Novikov spectral sequence. Now, those are big, complicated words, and they refer to some complicated algebraic machinery that I do not have time to go into in any detail in this talk. Let's just say the Adams-Novikov spectral sequence is an algebraic device, a machine for computing the homotopy groups of spheres. And I can't go into the details in this lecture. So you just have to take it on faith that there's this algebraic machine that calculates the homotopy groups of spheres. And its construction relies on the work of four Fields medalists, René Thom, John Milner, Serge Novikov, and Dan Quillen, that happened in the 50s and 60s. And you can read about this in my first book, Complex Cobordism and Stable Homotopy Groups of Spheres. I wrote the title in green because it's usually referred to as the Green Book. Now, Quillen in particular discovered an intimate connection between the cobordism theory of these complex manifolds, which include complex projective algebraic varieties, and some algebraic structures known as formal group laws. Formal group laws are either group or co-group objects in the category of schemes or something like that. I like to think of them as two variable power series over a ring R with certain properties. And again, I don't have time to, I'm not going to go into the technical details of this. They are well understood, and they were used by Lubin and Tate in local class field theory in 1965. And turns out that the construction in that paper turns out to be very relevant to the kind of homotopy theory that developed about 30 years later, 20 or 30 years later. Now, in particular, there's a graded ring associated with this known as BP star. BP stands for Brown and Peterson, the two men who invented this or discovered it. Anyway, it's a graded ring over the P local integers on generators V1, V2, etc. And the dimension of Vn is the number that is indicated there. So for each, you have this for each prime P. The problem of calculating homotopy groups is such that it's very easy to separate it into its P primary components for various primes P. So we're going to be almost this entire talk is going to be P local. You should we can focus on one prime P and make various statements. And there's over this ring, there's a certain formal group. There's a formal group law that has a certain universal property, and that's why it's important to us. And there's a functor. There's a way to assign to each space or spectrum X a module over this ring that is known as BP star of X. This is a generalized homology theory that assigns to each space or spectrum a module over this graded ring. And that's a crucial tool in this theory. Now, the next thing I want to talk about from the early 70s is Morava K theory. In the early 70s, Jack Morava discovered these spectra that are denoted by K of n and are referred to as Morava K-theories. And they are closely related to the Brown-Peterson spectrum BP. And I had the good luck to be able to spend a lot of time with Jack in those days. I first heard of him through a couple of very cryptic preprints that I got a hold of. And I remember the first time I held one of his papers in my hand, I thought to myself, boy, this looks really interesting, but I'll never understand it. There are just too many foreign concepts in this that are foreign to me. I'll never understand this. But a few months later, Steve Wilson introduced me to Jack, and I, after hanging out with Jack for enough, after hearing him explain these things often enough, I finally got it, and that was very, very helpful to me. Now, K of 0 is simply rational cohomology. That's something that we've understood for a long time. But for each positive n and each prime p, there's a non-connective, complex-oriented p-local ring spectrum called K of n that has its homotopy groups involve that polynomial generator V sub n that I mentioned before, and it's inverted. It's invertible in this ring. And it's related to something called height n formal group laws. It turns out that if you have a formal group law defined over something in characteristic P, there's an invariant attached to it called the height. I'm not going to I don't have time to give the definition here, but you can find it in the green book. The height is, if you're over an algebraically closed field of characteristic P, the height is a complete isomorphism invariant. And there's something called the Morava stabilizer group, which is the automorphism group of a height n formal group law, and it turns out to be very important in this theory. It's a p-adic Lie group, and it's the automorphism group of a height n formal group law over a suitable field of characteristic P. If you have any questions, please feel free to speak up and ask them. I'm going very fast, and I know some people in the audience are not homotopy theorists, so I hope this is not completely incomprehensible to you. But please ask me, please stop me with questions if you feel the need to do that. Now, the third thing that was caught my attention in those days was something called Smith-Toda complexes. So let's say n is a number n is 1, 2, or 3, and let's pick a prime that's sufficiently large in relation to n. Then Hiroshi Toda constructed a p-local finite spectrum that he called V of n, and it's a CW complex that has 2 to the n plus 1 cells in certain dimensions, and its BP homology is the quotient of the ring BP star by the ideal generated by P, V1, V2, and so forth through Vn. And he also found a cofiber sequence that looks like this. There's a map to Vn minus 1 from an appropriate suspension of Vn minus 1, such that the cofiber of that map is V of n. Now, why are these interesting? They're interesting because they give us a way to construct certain families of elements in the homotopy groups of spheres, as I'll spell out in more detail in a moment. But one thing we know about these is that the nth Morava K-theory on Vn minus 1 is non-trivial, and we know that that map, W sub n, induces an isomorphism in the nth Morava K-theory. That means that Vn has the same Morava K-theory as a point. And these lead to the construction of certain families of elements in the homotopy groups of spheres that live in the dimensions that are indicated here. For the three values of n, these elements are known as alpha sub t, beta sub t, and gamma sub t, and and with the appropriate lower bounds on primes. And so these are infinite families of elements in the mysterious homotopy groups of spheres. And I found this really, really interesting, and I wondered if there were more families like this, and what you could say, what else you could say about these. But these had sort of seemed to have fallen from the sky in the early 70s, and I was extremely curious about them. Now, in the E2 term of the Adams-Novikov spectral sequence, that's this high-powered algebraic machine for calculating these homotopy groups, you see these things displayed very nicely. And not only that, you see analogs of them for higher values of n. And this brings us to a paper that I wrote with Steve Wilson and Haynes Miller that appeared in 1977. This is the title of, this is a picture of the title of that paper. And this was our attempt to understand the work of Jack Morava. Now, in that paper, we constructed something called the chromatic spectral sequence, which is what you might call a pre-spectral sequence converging to the E2 term of the Adams-Novikov spectral sequence. Now, if you're not familiar with spectral sequences, this may sound very daunting, and I'm not going to be able to explain what spectral sequences are. Let's just say they're algebraic machines. In this case, there's two of them. There's one for calculating the homotopy groups of spheres, which it starts out with a certain algebraically defined gadget, and then you have to do some very difficult calculations to get from that algebraically defined gadget to the thing that you really want to know about, the homotopy groups of spheres. And the algebraically defined gadget itself is very hard to get at. And the subject of that paper was a way to get to the E2 term, the input for the Adams-Novikov spectral sequence. And that gadget was called the chromatic spectral sequence for reasons that I'll explain shortly. So it organizes things into layers in which the nth layer, everything is Vn periodic in some sense. The nth layer consists of periodic families like the three that I showed you a moment ago. And the structure of this nth layer is controlled by the cohomology of the nth Morava stabilizer group. Now remember, that's a p-adic Lie group that is the automorphism group of a height n formal group law. Now, we use the term chromatic because in each column of this spectral sequence, each value of n, it displays periodic families with varying frequencies. So this is like a this breaks up the homotopy groups of spheres into these periodic families, and it's sort of like a spectrum in the astronomical sense of the term. Now, I should point out that I'm using the word spectrum in this talk in two very different ways. I just mentioned the spectrum in the astronomical sense. So spectrum in the astronomical sense is something you get by taking the light from a star and running it through a prism and breaking it down into various wavelengths. And in those wavelengths, you might see certain lines and blah, blah, blah. That's a spectrum in the astronomical sense of the term. The term spectrum is also used in algebraic topology in an entirely different way. And a spectrum in the sense of algebraic topology, I've mentioned that word several times in this talk already. and it refers to a sequence of topological spaces with certain maps between them. And again, I don't have time to go into the details, but this is the objects of study in modern algebraic topology. Now, the paper by Miller, Ravenel, and Wilson was motivated by the examples of periodic families that I mentioned a few minutes ago. And each of them is constructed in the following way. So there's a finite complex V, such as the ones constructed by Toda, and some 3 different maps, as you see here. So the map in the middle, which I'm denoting here by lowercase v, is a map from some suspension of big V to big V. And the maps on the 2 ends are, the map on the left is a map from a sphere of some dimension into sigma d of V. And the map on the right is a map from V to to a sphere of some dimension. So the numbers K and L will be named later. So this has the following properties. One is, the most important is that the middle map D can be iterated. So the middle map V can be iterated. It's a map from the dth suspension of something to the dth suspension of V to V. And you could precompose that with its own dth suspension and get a map from the 2d suspension of V to V, and so on. You could iterate it as many times as you like. And in this situation, we know that all of these iterates are essential, meaning they are none of these iterates are null homotopic. They're all homotopically interesting. And what a map with that property is said to be periodic, because it leads to these periodic families. And we know that V has this property because it induces an isomorphism in the nth Morava K theory of the spectrum big V for an appropriate value of n. And examples have been constructed previously for n equals 1 by Adams, and for n equals 2 and 3, both by Hiroshi Toda and independently by Larry Smith. This was all in the 60s and 70s. So in the known examples, the map I on the left is the inclusion of the bottom cell into so in the known examples, that number little k was 0, and the number little l is the dimension of the top cell in that spectrum big V, which is a known, that dimension is a known quantity. So J was the map on the projection onto the top cell. And it's possible to show, in favorable circumstances, it's possible to show that the threefold composite is non-trivial, so you get an interesting element in the homotopy groups of spheres. So it was known in these examples that for each case, this composite is a non-trivial element. Now, there were only 3 examples known at the time, and they are the ones I just mentioned, constructed by Toda. So you have them for n equals 1, 2, and 3, and the primes, in each case, there's a lower bound on the prime. You don't have it for small primes. You only have it for suitably large primes. So this was in 1973. Now, 50 years later, we still don't have a V of 4. V of 4 has not, nobody has constructed a V of 4 to this day. So you might wonder, well, are there any more of these things? Are these 3 just a fluke? Is this just a fluke? Or is there somehow more of them? The fact that nobody's been able to construct V of 4 is somewhat you might think it's somewhat discouraging, but we'll find out later that it isn't really. Now, another thing is that in 2010, it was shown that Toda's hypothetical complex, where the number n is p+1/2 for your favorite prime, that never exists. You could never construct that particular complex never exists. So it means for example, if the prime is 5, v of 3 does not exist, nor do any of the higher v's. It's automatic that the higher v's can't exist. If v of 3 doesn't exist, this is for the prime 5, none of the higher ones can exist. And as I said, we don't know that v4 exists for any prime. Nobody's seen one yet. So the question is, are there more periodic families? Or are there any other periodic maps between finite complexes that are not detected by BP theory? That's another question you can ask. Are there, does BP theory detect them all, or are there some that aren't, that BP theory doesn't see at all? Or another question you could ask is, what would happen if we replace that ideal that I mentioned by a smaller ideal? What would happen if we took that ideal and replaced some of the generators of it by powers of those generators? That's what I mean by a smaller ideal, and tried to do the same thing. And then we might get a finite complex with a self map inducing multiplication by some power of VCN rather than, or V sub n rather than V sub n itself. So these are all questions that I was wondering about at the time. And again, we're still in the 70s. Now, I'm going to say a little bit more about what goes on in that chromatic spectral sequence that I mentioned. There's something called BP lower star BP, which is the analog of the dual Steenrod algebra in this game. And it has an algebraic structure called it's a Hopf algebroid. And again, I don't have time to go into that here, but it's all written down in the green book. And the Adams-Novikov E2 term is an X group defined in terms of this gadget. Now, it turns out that the way to study this is to look at a certain long exact sequence called the chromatic resolution, and I will say more about this in a moment. So the long exact sequence starts with BP star. It gets included into a larger gadget called M upper 0, and then that maps to M upper 1 to M upper 2 and so forth. And this is a long exact sequence. And if you have a long exact sequence like this, then it's an exercise in homological algebra to show that you get a trigraded spectral sequence converging to the Adams-Novikov E2 term, and the input has to do with X groups for those yet to be defined modules M0, M1, M2, M3, and so forth. And again, this X group, the X group associated with the nth module in this sequence, is somehow related to the cohomology of that nth Morava stabilizer group, the automorphism group of a formal group law of height n. And it's also related to Vn periodic phenomena, whatever that means, in the stable homotopy groups of spheres. And again, I'm using the term chromatic because it's separating. It's like you have all this noise in the form of the homotopy groups of spheres. When you first encounter it, it looks very chaotic. It looks very noisy, but you can separate it into various frequencies like you do in astronomy with starlight. Now, so what are these modules? M0 is obtained from BP star by inverting the prime P. Remember that BP star was a polynomial algebra over the integers localized at P on certain generators. And so you could invert P, or that's the same thing as tensoring everything with the rational numbers. And then you would get so you could include BP star into its tensor product with the rationals, and then you'd get a certain co-kernel that I'm going to call BP star mod P infinity. Now, Peter Schulze said that notation baffled him. But what I mean by that, what is meant by that is you could take BP star mod P to the I, or not, let's just do this for, let's just do this for the integers. You could take Z mod P to the I and include it into Z mod P to the I plus 1 in an obvious way, and then include that into Z mod P to the I plus 2, and then you could take the co-limit of all of that, and you'd get something known as the Prüfer group, which I like to call Z mod P to the infinity. So Z mod P to the infinity means the co-limit of Z mod P to the I as I gets larger. Okay, now, sorry, getting ahead of myself here. Okay, now, for larger n, let's say we constructed big N upper little n. So here is n upper 1. That's BP star mod P infinity. At the next stage, we're going to want to invert V1 in here and so on. Okay, so Mn is obtained from n upper n. This is an inductive construction, and at the nth stage, we want to invert little vn. And we'll get these short exact sequences of BP star modules. Now, so if I have these short exact sequences for each n, I can splice them together and get the long exact sequence that is indicated here. So this is obtained by splicing together all these short exact sequences. Now, this construction is purely algebraic. It's a construction that I've done in the category of BP star modules equipped with certain additional structure, algebraic structure. The question is there a similar construction in the stable homotopy category? That's the real question. Is there a similar construction in the stable homotopy category? And so the beautiful, does it have the same kind of algebra associated with it that we've seen here? Or is this wonderful algebraic structure just an artifact of complex cobordism theory? That's the deep underlying, that's the question that I asked myself in the 70s after writing this paper with Miller and Wilson. And this question occupied me for the next several years. And it resulted in this paper that appeared in 1984. And I'm going to read you the opening paragraph of it. This paper represents an attempt, only partially successful, to get at what appear to be some deep and hitherto unexamined properties of the stable homotopy category. This work was motivated by the discovery of the pervasive manifestation of various types of periodicity in the E2 term of the Adams-Novikov spectral sequence, converging to the stable homotopy groups of spheres. And then I mentioned a couple of papers there, 34 and 41. 34 is the paper with Miller and Wilson that I mentioned before, and 41 is an expository paper that I wrote around the same time called The Novice's Guide to the Adams-Novikov Spectral Sequence. There is not a reference here to the Green Book because the Green Book hadn't been written yet. Now, Okay, so it says, in those papers, we introduced the chromatic spectral sequence, which converges to the above E2 term. Unlike most spectral sequences, its input is in some sense more interesting than its output, as the former displays many appealing patterns which are somewhat hidden in the latter. It is not so much a computational aid, although it has been used for that to calculate the Novikov two-line. It's not so much as a computational aid as a conceptual tool for understanding certain qualitative aspects of the Adams-Novikov E2 term. So here again are the short exact sequences that can be spliced together to give you this long exact sequence, which leads to this interesting algebra. And it would be nice if each of those short exact sequences were the BP homology of a cofiber sequence of spectra. It would be nice if such things existed. Then that if there were, we would have spectra that I call M sub n and big N sub n that have the property that the BP homology of M sub n is this module up here, M upper n, and similarly for the n's. Now, this is easy enough to do in the n equals 0 case, because we remember the way we got from BP star to M0 is we just inverted the prime P, and we know how to do that in the homotopy theoretic world. So that's not a problem. But the next stage, we need to invert V1 somehow, and that's not clear. It wasn't clear at the time how one might go about doing that in the world of spectra. We know how to do it in the algebra world, but it wasn't clear how to do it in the topological world. Now, as luck would have it, the perfect tool for this was invented at exactly the right time by Pete Bousfield. Pete Bousfield was a very soft-spoken, shy, retiring, but absolutely brilliant mathematician that I was lucky enough to have as an instructor when I was in graduate school at Brandeis around 1970. Anyway, after that, he invented the perfect tool for this purpose. And it is something now known as Bousfield localization. And this is the title of his paper that he published in 1979. Perfect timing. So I'm going to tell you a little bit about what he did in this paper. So let's say we have a generalized homology theory represented by a spectrum E. So E could be Morava K theory, it could be complex cobordism, it could be this, it could be that. We'll say a spectrum Z is E local if, whenever you've got a map between two other spectra that induces an isomorphism in E homology, then it also induces an isomorphism in homotopy classes of maps into Z. Now, F is a map from A to B that induces maps going the other way between the things indicated here. If you have a map from B to Z, you can pre-compose it with F and get a map from A to Z. So that's what this map F upper star means. Okay, so the condition, we say that a spectrum Z is E local if whenever you have a map like this inducing an isomorphism in homology, it also induces an isomorphism in these groups here. That's what it means to be E local. Now, it's not immediately obvious that there are any E local spectra out there. This is not obvious that such things exist at all. But anyway, we can make this definition. Now, here's the theorem that Bousfield proved in that paper. he says, you can always find an E-local, there's plenty of E-local spectra out there. And not only that, you can start with any spectrum X and find an E-local spectrum that's known as LE of X and a map from X to that thing, which is an E star equivalence. Now, to me, this was a bolt out of the blue, and I did not understand how he proved this. And for the next 30 or 40 years, I treated this theorem as a black box. I made extensive use of it, but until I only learned how he actually proved this about 10 years ago. I treated this as a black box for most of my career. And anyway, it's an amazing theorem, and it's turns out that it's the tool that we need to do chromatic homotopy theory. Okay, so what is this? What does this thing LE of X look like? Well, it turns out that if E and X are both connective spectra, meaning if they both have no homotopy groups below some fixed dimension, say below dimension 0, then LE of X can be described in arithmetic terms, by which I mean you can do something arithmetic to X. You either invert some primes or maybe you complete at a single prime. And we already understood how to do this at the time. Inverting primes or completing at a prime was something that was had been around for a while. So this is not this is not surprising. That is, if E and X are both connective. But if either of them fail to be connective, then things get much more interesting. And the spectra that are given by Bousfield's theorem become much more interesting and mysterious. So remember that we were trying to do an inductive construction. We were trying to construct a hypothetical spectrum M sub n. And what if that could be obtained from the inductively constructed n sub little n by some form of Bousfield localization? That's what I was hoping for once I learned about Bousfield's theorem. Now, the logical choice for the E that would do this appears to be the Johnson-Wilson spectrum, E of n. So what is that? I believe Johnson and Wilson are both here today, so they know the answer to this. So it's a BP module spectrum whose homotopy is, we take the homotopy of BP star, we invert Vn, and then throw away all the higher generators. Now, throwing away the higher generators isn't really necessary for this purpose. The important thing is that Vn gets inverted. And this is related to a fancier gadget called the Morava spectrum En, but it hadn't been invented yet. Now, it turns out that both lead to the same functor L sub E. So let me go back to Bousfield's definition. Remember that a spectrum is E-local if this condition is satisfied. Now, this condition is equivalent to another condition. If a spectrum C is E acyclic, meaning that its E homology is 0, then all maps from it into Z are null homotopic or homotopic to the trivial map. So that's an equivalent condition on Z. So here's a definition. We're going to say that two spectra E and E prime are equivalent, Bousfield equivalent, if they lead to the same class of acyclic spectra. That is, the E star homology of C vanishes if and only if the E prime star homology of C vanishes. So this is a very coarse equivalence relation on spectra. This is very far removed from homotopy equivalence. It's a much coarser equivalence relation. And I'm going to denote the Bousfield equivalence class of E by these pointy brackets. And I'm going to define a partial ordering of these equivalence classes. I'm going to say that the class of E dominates that of F if being E acyclic, if E acyclicity implies F acyclicity. So this means the E homology gives at least as much information as F homology. And it follows that there's a maximal Bousfield class, which is that of the sphere spectrum, and there's a minimal Bousfield class, which is that of a point. And then there's lots of stuff in between. Now, all of these definitions were made in Bousfield's original paper, and he proved some very interesting things about this notion of Bousfield equivalence. One is it's easy to check that wedges and smash products are well defined. That is, we can say the wedge of two equivalence classes is the equivalence class of the wedge, and similarly for the smash product. And then we can say that here's some formal properties of these things. If you have a cofiber sequence like this, W to X to Y, to suspension of W, then the Bousfield class of X is dominated by that of W wedge Y. The Bousfield class of X is dominated by that of the wedge of W, the two things on either side of it. Another formal property is that if the map F is smash nilpotent, if this map is smash nilpotent, which means that if you take the k-fold smash product of the source and target, you get a map that's null for some value of k. That's what it means to say that F is smash nilpotent. If that happens, then the inequality that we had before becomes an equality. Third, if you have a map from some suspension of X to X, now remember, we saw these kinds of maps before when we were constructing periodic families in the homotopy groups of spheres. So let's say we have a map like this, and we'll call the cofiber of it C sub V. And then by iterating this map, we can get a colimit, which is also known as the mapping telescope, which I'll call X hat. So if you have such a map, it has a cofiber C sub V and a telescope X hat. And what you can say is that the Bousfield class of X is the wedge of that of the telescope and the cofiber, and the smash product of those two is zero. The smash product is contractible. So these are formal properties of Bousfield classes. It's not very difficult. These are all easily proved. Now, here are some examples of such things. One is the Bousfield class of the sphere spectrum, which, as I mentioned, is the maximal element. Now, it turns out that that is equal to the wedge of the rational sphere and all the mod P spheres, all the mod P Moore spectra. And it turns out that the Bousfield class of the sphere has this decomposition, and it turns out that if you take any two things, this is an infinite wedge. So this is on the left, we have an infinite wedge of things. We have the rational sphere, and then we have the mod P sphere for all primes P. So this is an infinite wedge decomposition. And it turns out that the smash product of any two of those wedge summands is contractible. Here's another one. the Bousfield class of BP dominates this. H mod P means the mod P Eilenberg-MacLane spectrum, and Kn is the Morava K theory that I mentioned before. And then a third one is that this Johnson-Wilson gadget E of n is Bousfield equivalent to the wedge of the first n+1 Morava K theories. And in each case, the smash product of any two of the wedge summands on the right is contractible. So in other words, in each case, this is sort of an orthogonal decomposition of the Bousfield class on the left. Now, here, it's only an inequality. The Bousfield class of BP is greater than or equal to this. It's not equal. It's not actually equal, but these two are equalities. Now, the localization functor associated with E is determined by this Bousfield class. And when E, the Bousfield class of E dominates that of F, there's a natural transformation from LE to LF. Now, for a fixed prime P, let's let Ln denote Bousfield localization with respect to En. Then for any spectrum X, we get a diagram like this. So there are various localization functors. I haven't told you what L infinity is, but anyway, this is known as the chromatic tower of X. L infinity denotes localization with respect to the wedge of all the Morava K theories. And this is known as the chromatic tower of X. And that this raises some questions. So one question is, when is the map from X to L infinity in equivalence? Maybe it is, maybe it isn't. When it is, we'll say that X is harmonic. That's the definition of the term harmonic. X is harmonic if it's local with respect to the wedge of all the Morava K theories. And that's called the harmonic localization of X. If that, it may be that the opposite may happen. It may be that L infinity of X is contractible, and in that case, we say X is dissonant. That's supposed to be the opposite of harmonic. Another question you could ask is, what about the inverse limit of all these LNs? What about the homotopy limit of all those LNs? That's not the same as L infinity. So another question we can ask is, when is the map from X to that homotopy limit of the Ln of X? When is that an equivalence? And this is called the chromatic convergence question. We'll say that X is chromatically convergent if that happens. So these are two adjectives that you can apply to a spectrum: harmonic and chromatically convergent, and it has to do with the behavior of X under these Bousfield localization functors. And another question is, can we describe the BP homology of Ln of X in terms of the BP homology of X? And this is called the localization question. Now, remember, L infinity denotes localization with respect to the Bousfield class of the wedge of all the Morava K theories. Now, a p-local spectrum is said to be harmonic if it's equal to, if X is equivalent to L infinity of X, and it's dissonant if L infinity of X is contractible. So that means that a spectrum is dissonant if all the Morava K theories vanish on it. Now, it follows from the definitions that there are no maps, no essential maps from a dissonant spectrum to a harmonic one. So one example of a dissonant spectrum is the mod P Eilenberg-MacLane spectrum. So in the 84 paper, I showed that every p-local finite spectrum is harmonic. I also showed that a p-local connective spectrum is harmonic if the BP homology has finite projective dimension as a BP star module. And I showed that the mod P Eilenberg-MacLane spectrum is dissonant. This is the same for any spectrum whose homotopy groups are all torsion and are bounded above. If you have a spectrum where there are no homotopy groups above a certain range and all the homotopy groups are torsion, then any such spectrum is dissonant. Now, as I said before, a spectrum is chromatically convergent if it's equivalent to the homotopy limit of this diagram. Around 1990, Mike Hopkins and I showed that p-local finite spectra are chromatically convergent. So that includes the sphere spectrum. It's chromatically convergent. And proof can be found in the Orange Book of 1992. In 2014, Toby Bartle showed that a p-local connective spectrum X with finite, whose homology has finite projective dimension is also chromatically convergent. Now, I showed that such a spectrum is harmonic. He proved the stronger theorem that it's chromatically convergent. Now, one of the original questions in this lecture was, does the chromatic resolution leading to the chromatic spectral sequence of Miller, Ravenel, Wilson have a geometric underpinning? That was the question. More specifically, is the short exact sequence that looks like this the BP homology of a cofiber sequence? My hope was that there are spectra Mn, M sub n, and N sub n with these properties, and that M sub n is obtained from N sub n by Bausfield, the nth Bausfield localization functor. Now, we have these Bausfield localization functors, so we could use them to construct something in this way, but how do we know that they have the right BP homology? In other words, how do we calculate the BP homology of these things? So this is a special case of the localization question, which was how to describe the BP homology of Ln of x in terms of that of x itself. Now, it turns out that it's not hard to figure out what you get if you apply Ln to BP itself. So this means it's easy to understand the spectrum that you get that by smashing X with Ln of BP. Now, here's a theorem that was a conjecture in the 84 paper, and it goes like this. For any spectrum X, the smash product of BP with Ln of x, that is the BP homology of Ln of x, is the same as the smash product of x with Ln of BP. So in particular, if En minus 1 of x happens to be 0, then the BP homology of Ln of x is, you get that just by inverting Vn. And that's exactly what I was hoping for. This means that the chromatic resolution can be realized geometrically as I had hoped. Now, it turns out that this functor Ln satisfies a much stronger condition, which Yuri Salima obliged by illustrating with a cartoon. So this was conjectured in 1984 and proved by Hopkins and me a few years later, and the proof is in the Orange Book. Anyway, when your localization functor LE has the property that localization the LE localization of X is the same thing as the smash product of X with the localization of the sphere, we say that E is smashing. And the theorem is that En is smashing in this sense. So the paper, the 84 paper, ended with a list of about 10 conjectures, and all but one of them was proved within the next 15 years. The one that wasn't proved was the telescope conjecture, which I'm going to discuss in a moment. Anyway, they were all proved within 15 years, mostly by Mike Hopkins and various collaborators. Now, I've already mentioned some of them, and I'm going to state some more of them as theorems. So one is the nilpotence theorem. So this was conjectured in the 84 paper and proved by Devenants, Hopkins, and Smith in 1988. So it says the following. If you have a finite spectrum X and a map from some suspension of X to itself, it's nilpotent, meaning some iterate of it is null homotopic, if and only if the corresponding map in mu star homology is nilpotent. Now, if you're in the P local world, you can replace mu by BP. Okay, so we can talk about the nilpotence of a map from a gadget to itself, or we could talk about the smash nilpotence of a map from X to Y. So remember what that meant. That means a map is smash nilpotent if you take some smash power of everything in sight. If that map is if the k-fold smash product of the map is null for some k, then that's what then we say that the map is smash nilpotent. Now you can make a similar discussion for you could smash everything in sight with mu and ask for a similar condition, and it turns out that a map G like this is smash nilpotent if and only if it's if its smash product with mu is null homotopic, or if, not if and only if, sorry, if the smash, if mu homology doesn't see the map, if the map is trivial in mu homology, that means it's smash nilpotent. And a third condition, if you have a connective ring spectrum and you have an element in its homotopy, we could, if H isn't, we have a map from the homotopy of R to the mu homology of R, then we can say that an element in the homotopy of R is nilpotent when its image in the mu homology is 0. And fourth, if you have a cofiber sequence where this last map is trivial in mu homology, then the Bausfield class of X is equal to that of the wedge of W and Y. In other words, the Bausfield class of X is what you would get if this map F was actually null homotopic. If F were null homotopic, then X would be W wedge Y. This says that if the map F is trivial in mu homology, then the Bausfield class of X is equal to the Bausfield class of W wedge Y. Now, one thing I knew in 1984, oh, I'm sorry, there's some, just looking at, I'm looking at the Somebody asked, will the PDF file of this presentation be available online? I will certainly place it on my website. And Shrikar, if you want to do so, if you want this PDF file, I will give it to you.
Yeah, great. Yeah, we can put it up as well.
Okay. Sorry, I just noticed the chat. Okay, there's a natural transformation from the identity functor to the localization functor. Oh, somebody asked, what does co-augmented mean? I'm sorry, I didn't see that sooner. Co-augmented means that there's a natural transformation. It means that there is a natural transformation, as Andy described. That's what co-augmented means. Sorry about that. Okay, now, one thing I figured out in the late 70s, that if it were the case that the Bousfield class of MU was the same as the Bousfield class of the sphere, then the theorem I just mentioned would follow automatically. The nilpotence theorem would follow immediately if the Bousfield class of MU was the same as the Bousfield class of the sphere. In other words, if MU sees everything, then the nilpotence theorem that I just mentioned would follow immediately. However, this is not the case. There's a strict inequality between the Bousfield class of BP and that of the p-local sphere spectrum. And there's a similarly, the Bousfield class of MU is strictly smaller than that of the Bousfield class of the sphere. So this means there are BP, there's such a thing as a p-local spectrum with trivial BP homology, but it's not contractible. There are non-contractible spectra that are BP acyclic. In other words, MU does not see everything. And it's actually worse than that. There are spectra called T of M, p-local connective spectra T of M for each non-negative M that have this condition. The BP homology is polynomial algebra on the first M little t's, and there are strict Bousfield inequalities that go like this. So there are infinitely many steps to get from the Bousfield class of the sphere spectrum to the Bousfield class of BP. There are infinitely many many steps in many Bousfield inequalities like this. Now, the nilpotence theorem but nevertheless, the nilpotence theorem is true, even though it's not a purely formal argument as I had hoped. If it was the case that the MU had the Bousfield class of MU was that of the sphere, then the nilpotence theorem would be a formality. Now, it's not true that the Bousfield class of MU is that of the sphere. There's a strict inequality there, and the proof of the nilpotence theorem is not a formality. It involves some serious computation. Now, let's go to so this is one part of the nilpotence theorem. It says for a finite spectrum X, a self map is nilpotent if and only if it's nilpotent in BP homology. This means that such a map can be periodic, the opposite of being nilpotent, if and only if MU homology sees it that way. And in the p-local case, this means that some Morava K theory has to see it. If it's periodic, it has to be seen by some Morava K theory. Now, here's a theorem proved by Hopkins and Smith published in 1998. I'm sure they knew it long before, probably a decade or more before that, but it goes like, it says the following. Let's say you have a p-local finite spectrum of chromatic type N. That means that Kn minus 1 vanishes, but Kn, the nth Morava K-theory, is non-trivial. That's what type N means. Then there is a map, what we call a Vn self-map. There is a map from some positive suspension of X to X that induces an isomorphism in Morava K-theory. But the corresponding map in ordinary mod P homology is 0. There is such a map. Now, if n equals 0, then d has to be 0. If n is positive, then d has to be a multiple of this number. Now, now there's also a uniqueness statement here. It says if we have a second map with a similar property, then you can find numbers I and j such that the ith iterate of one map is equal to the jth iterate of the other map. So in other words, this map V is asymptotically unique. So this is known as the periodicity theorem this is the Hopkins-Smith periodicity theorem. Now, it follows that the cofiber of V, little v, of this self-map little v, or any of its iterates, is a p-local spectrum of chromatic type N plus 1. So with that spectrum, we could do the same thing. We could look for a self-map of it that induces an isomorphism in the N plus 1th Morava K-theory, and so on. So this means there are finite complexes of all chromatic types, and Steve Mitchell was the first person to construct finite complexes of arbitrary chromatic type. But anyway, this means that there are lots of periodic families in the homotopy groups of spheres, not just the 3 that we knew about in the early 70s, but lots and lots of them, with all flavors of periodicity occurring. Now, here's a pleasant consequence of the nilpotence theorem. I called it the class invariance conjecture in the 84 paper, and it is that the Bausfield class of a p-local finite spectrum is determined by its chromatic type. That determines the Bausfield class of such a thing. In particular, it means that if you have a finite spectrum whose homology is not all torsion, then its Bausfield class is that of the sphere. Now, I'm going to talk about the telescope conjecture. This is the one conjecture that was not proved by Hopkins within a few years. So let's say we have a p-local finite spectrum of chromatic type N. That means that it has this Vn self-map that I'm calling little v. And this map can be iterated, and we get a telescope associated with it, like this. All right, so we'll call that x hat. Now, all of these maps here induce isomorphisms in the nth Morava K-theory, and that means they also induce isomorphisms in the Johnson-Wilson En, and that means that we have a map from x hat to Ln of x. So Ln of x is the En localization of x, and in this case, that's the same thing as the Kn localization of x. Now, the telescope conjecture says that this map is an equivalence. That's the telescope conjecture. It says that that mapping telescope is the same thing as the En localization. Now, let me go back to this previous slide here. The significance of this is Ln of x, if x is has chromatic type N, then ln of x is something we know how to get our hands on. It's accessible to computation. We can figure out, we know a lot about it. On the other hand, this mapping telescope is more closely related to the homotopy groups of spheres, because in some sense, the mapping telescope is going to see all of the Vn periodic homotopy of X. This ln of X might see only some of it, but X hat will see all of it. So this gadget here is, this X hat, this telescope, is more geometrically interesting, but while this ln of X is more computationally accessible. So it would be really nice if those two were the same. And that's what the telescope conjecture is about. Now, so it's a different statement for each prime and each n. Now, this is trivially true for n equals 0, because in that case, you're just inverting a prime. And for n equals 1, it was proven by around 1980 by Mohold for the prime 2 and by Haynes-Miller for odd primes. So this was proved in the around 1980 for n equals 1. For n bigger than 1, it was a big mystery. Now, this brings us to the fall of 1989. At that time, there was a homotopy theory program at MSRI in Berkeley. Now, I know it's since changed its name to Simon's Law for Math. But anyway, it was known then as MSRI, and there was a lot of homotopy theorists there. I was there, and I was thinking very hard about this question, about the telescope conjecture. I wanted very much to prove it. And then something happened that led me to think it might not be true. It may actually be false at larger values of n, larger than n equals 1. Something happened that made me think that. And this is the something that happened. There was a big earthquake. There was a big earthquake during this program, October 17th, San Francisco earthquake of October 17th, 1989. This is some damage it did to the Bay Bridge. You can see this section of it, this collapsed here. This is earthquake damage. But anyway, I like to say this is earthquake mathematics, because it was within a day or two of this earthquake that I got an idea about how I might disprove it for n bigger than 1. Now, I was never I had an idea about how to do this then, but I was never actually able to follow through on it. So in 1989, I began to think this was false, and I spent the next 30 years or more trying to do this, never succeeded. But now it's a theorem by Robert Birkeland, Jeremy Hahn, Ishan Levy, and Tomer Schlenk. And there is a picture. They announced their theorem at Oxford in June of last year, and this picture was taken then. So that is the end of my talk. Thank you very much.
Yeah, this is does anyone have any questions that they want to ask?
What have we got? Oh, okay. You're welcome.
Is there some upsides to the fact that the telescope conjecture is false?
It means that it's another instance of I've said the following in various letters of recommendation for various algebraic topologists. I'm trying to describe what this subject is like, about the problem of calculating the homotopy groups of spheres. And what I've said many times is that every decade or two, there's a big breakthrough in the subject. We learn a lot more about how to calculate homotopy groups of spheres than we knew before. And every time this happens, we learn that the actual answer is a lot more complicated than we thought. Every time there's a big breakthrough in the subject, it tells us that the answer is far more complicated than we had appreciated before. And this is another instance of that. So, so I don't know if you consider this an upside or not. This depends on your temperament. But let me go back to the statement here. Okay, so as I said, for n equals 2, so let's think about the simplest non-trivial example of this, and that would be the case where X is the tota complex. We're doing this for n equals 2, the prime's at least 5. X is the the complex constructed by tota, known as V of 1. It's a CW complex with 4 cells in certain dimensions. Now, we know what the homotopy of L2 of that X is, and we know that it has 12 periodic families in it. 12. We know how to calculate this. On the other hand, that X hat is likely to have infinitely many periodic families. Now, you can decide whether this is an upside or a downside. That's your choice. But the X, the homotopy of X hat is a lot, at least my guess is that it's a lot more complicated than that of ln of X. I know what ln of X looks like. Now, the BHLS, that is Robert, those guys, tell me that the actual complexity, there's a huge Picard group involved in this. I don't fully understand this. I'm not sure they do either, but they say there's a gigantic Picard group in the picture here. But anyway, it means that the mystery of this, there's a lot more mystery to this than we thought. And that's why I don't think the problem's going to, I don't think that, I think that this is not going to be solved in the lifetime of my granddaughters.
Okay.
And I'm hoping they have nice long lives, but I don't think they'll live to see a complete determination of the homotopy groups of spheres.
Mhm.
I was wondering about, I'm sorry, Professor Ravenel, I was wondering about, you said Busfield localization, it kind of came at an opportune moment in 1979, and I was kind of wondering about, was Busfield thinking about similar problems? It kind of seemed somewhat magical to appear at the right.
Yes, well, he was thinking, he and Dan Kahn had written a book affectionately known as the Yellow Monster, called Localization, Completion and Limits and Homotopy Theory, or something like that. It's a Springer volume published in 1972. Dan referred to it as the Yellow Monster. Dan had a good sense of humor. He wrote another book with some other co-authors a few years later that he referred to as the Blue Beast. But anyway, the Yellow Monster said a lot about, they were interested in various kinds of localization. And I remember Dan telling me that Busfield proved his theorem just a couple of years after they finished that book. It was too late to be in the book, but there had been various attempts to do localization theory, various kinds of localization before then, and Busfield's theorem blew them all away. So he was working on this kind of thing independently of chromatic homotopy theory. He was thinking about it for his own reasons, I believe. Now, 6 things in the, open the chat window again. Okay, somebody asked, did the BHLS proof follow your original plan of attack? And my answer to that is absolutely not. They use techniques that I never would have thought of. It involves algebraic K-theory and cyclotomic spectra, and cyclotomic is redshift, it's a fantastic collection of mathematics, but it's nothing I could ever have done. It's not like I did have a program for proving it that I could never make work, and it's not like they found the missing piece of my program. No, they did something completely different. So I'm very happy about that. Their proof is not at all like what I had in mind. And okay, what happened to make you think the telescope conjecture was false for n bigger than 2? Well, I started doing some calculations that led me to think that there's infinitely many periodic families instead of just 12 in the simplest case. So what is this are we still recording? Oh, this link is where the recording is going to appear. Is that right?
Yeah, the
Okay.
YouTube channel.
Yeah. So there's a recording, there's a video, and I will make the PDF file available.
Are there any more questions?
Well, thank you all for coming.